Welcome to a deep dive into the statistical bedrock of machine learning, resampling methods. As practitioners, our ultimate goal is to build models that not only perform well on the data they've seen but, more crucially, generalize effectively to unseen data. This challenge of robustness and generalization is precisely where techniques like bootstrapping and cross-validation become indispensable tools in our arsenal. The fundamental problem we face in machine learning is accurately estimating a model's true performance. A simple train-test split, while foundational, often provides a single-point estimate that can be highly sensitive to the specific data points included in each set. This variability makes it difficult to ascertain how robustly our model will behave in the real world, especially with limited data. Resampling methods address this by repeatedly drawing samples from a training dataset and refitting a model on each sample. This iterative process allows us to create multiple versions of our model's performance metrics, providing a more comprehensive and statistically sound understanding of its capabilities and limitations. They are vital for generating reliable performance estimates. Let's begin with bootstrapping, a powerful, non-parametric resampling technique. The core idea is elegantly simple. To simulate having multiple datasets from the same underlying population, we repeatedly sample from our observed dataset. This means each data point has an equal chance of being selected for each resample, and can be selected multiple times. Imagine having a dataset of 100 observations. To create a bootstrap sample, we would randomly pick 100 observations from our original set, allowing for duplicates. This process is then repeated hundreds or even thousands of times, generating a large collection of bootstrap samples, each slightly different from the others. With these numerous bootstrap samples, we can train our model on each, calculating performance metrics like accuracy, precision, or recall for every iteration. By analyzing the distribution of these metrics, we can not only derive a more stable estimate of the model's average performance but also construct confidence intervals, giving us a crucial range for our model's expected behavior. The advantages of bootstrapping are significant. It's particularly useful when dealing with smaller datasets where a traditional train-test split might lead to unstable evaluations. Furthermore, it's distribution-free, meaning it doesn't assume any specific underlying distribution for the data, making it highly flexible across various data types and model complexities. Now, let's shift our focus to cross-validation, another cornerstone of robust model evaluation. While bootstrapping samples with replacement, cross-validation partitions the dataset into distinct subsets. Its primary goal is to assess how well a model will generalize to an independent dataset by systematically rotating through different train and test splits. The most common form is k-fold cross-validation. Here, the dataset is divided into k-equal-sized folds. The model is then trained k times. In each iteration, one fold is reserved as the validation set, and the remaining k1 folds are used for training. This ensures every data point gets to be in a validation set exactly once, and in a training set k1 times. Variations of cross-validation also exist, such as stratified k-fold, which ensures that each fold maintains the same proportion of target variable classes as the original dataset, crucial for imbalanced datasets. Leave one out cross-validation, an extreme case of k-fold where k equals the number of data points, provides nearly unbiased estimates but is computationally very expensive. A key advantage of cross-validation is its efficient use of data. Unlike a single train-test split, it leverages all data points for both training and validation across different iterations, leading to less biased and more stable performance estimates. It's also excellent for hyperparameter tuning, allowing us to select the best model configuration without overfitting to a single validation set. While both bootstrapping and cross-validation enhance robustness, they serve slightly different purposes. Bootstrapping excels at providing confidence intervals for performance metrics and handling smaller datasets. Cross-validation is generally preferred for model selection, hyperparameter tuning, and obtaining a single, reliable estimate of generalization error. In practice, these methods are often used in conjunction or sequentially. For instance, cross-validation can be used to select the optimal hyperparameters for a model, and then bootstrapping can be applied to the final chosen model to derive robust confidence intervals for its performance metrics. This layered approach maximizes our confidence in the model's predictive power. Ultimately, mastering resampling methods like bootstrapping and cross-validation is not just about understanding statistical theory, it's about building more reliable, trustworthy, and deployable machine learning models. They move us beyond superficial performance numbers to a deeper understanding of our model's true generalization capabilities, ensuring they stand up to the rigors of real-world application.